Welcome everybody to our show today. Let me just make sure everything is going all right. There we go. I'm watching on YouTube just like you, just to make sure it's just a little bit of delay there. So welcome to our show from I&E on deciphering spanning tree topologies today. And I'm Keith Bogart. I'm one of the instructors here. I specialize in the routing and switching CCNA and CCNP level videos, and it's my pleasure and enjoyment to, in our time together today, to hopefully make you guys experts on figuring out how spanning tree creates a tree, how it decides which ports are forwarding, which ports are blocking, and if something changes on a switch, like an entire switch crashing or a new port coming up or going down, how that affects things and how that changes the tree, if at all. So in the event that you have not seen any videos from me before, let me just show you here. Here's my contact information. So I'm going to do my best throughout this session to answer any questions that you post to YouTube Live. In the event that I'm not able to get to your questions, if there's just too many of them or something, feel free to reach out to me there. You see my email address and Twitter account and LinkedIn, and through that you can reach out to me. Now let me just, sorry, I am recording today's show as well, and there we go. So let me just briefly sort of describe the audience that I'm going to be speaking to for today's show, because I realize that those of you who are watching come from lots of different backgrounds, lots of different experience levels. So the audience I'm really going to be speaking to today are people who are primarily learning spanning tree for the first time, for the purposes of like getting their CCNA certification. Or maybe you got your CCNA certification routing and switching a while ago. Now you're pursuing your CCNP. And the exam you're going for right now is a CCNP switch exam, which also expects you to thoroughly understand spanning tree. But maybe it's been a while since you did your CCNA and you forgot how spanning tree works. So either way, that's the core audience that I'll be speaking to today. So now, like I said, there's a lot of people with different experience levels and technical knowledge who are watching this. So by all means, submit whatever question you have during the YouTube live session today. I just want you to be aware that if the question you submit is really out of the scope of this class, for example, if you start asking me something about multiple spanning trees, or how rapid spanning tree is different than 802.1d, or asking me questions about uplink fast or backbone fast or stuff like that, those are all really interesting questions and definitely stuff you do need to know for various certification tests. But our time is very limited today, and that is outside the scope of what I'm going to be covering. So I would still encourage you to ask your questions, and even though I might not have an opportunity to get to questions like that, because I'll be focusing more on questions that are within the scope of the class, there's a very good chance that if you ask whatever question you have, somebody on the YouTube live feed will answer you. So if you're watching, and if you do see someone post a question and you think, hey, I have experience in that field, or I know the answer to that, feel free to pipe in and type in an answer to that person and help everybody out. So I'm not the only one here. We can all learn from each other's experience in today's class. So with that, let's go ahead and get started here. And I'm going to be doing today's class in a variety of ways. First of all, I'm going to be making extensive use of whiteboarding. So I'm actually using Cisco's WebEx tool, and it's got a whiteboarding feature within that I just like to use, so I'll be doing that. And for demonstrations, I'll be doing demonstrations primarily on Packet Tracer. And the reason I'm doing that is because for those of you watching, if you don't have any experience with Packet Tracer, it's absolutely free. You can download Packet Tracer for free. All you need to do is sign up for Cisco's Networking Academy, which basically just entails giving them your username, password, and email address, and that's pretty much it. And then you can play around with spanning tree and do most of the stuff I'm going to show you today, so you could follow along with me. Or once the recording of this comes out, you could follow along with the recording. But I figured Packet Tracer would give everybody throughout the world the opportunity to do this stuff because it is freely available. Now, the downside with Packet Tracer is because it's not real Cisco iOS software, it doesn't have all the commands available the real Cisco iOS software has. And a lot of times when you issue show commands, like, show this protocol or show that, the output that you get is not exactly the same as the output you get in a real switch. So there will be times that I'll be moving over to our INE lab racks here, where I can actually show you on real switches and sort of do a comparison and contrasting between this is what you would see on Packet Tracer, this is what you'd see on a real switch, and here on the real switch you can see you've got some additional options that allow you to do some things that Packet Tracer doesn't allow you to do. But I will try to keep most of my demonstrations constrained to Packet Tracer if at all possible, since I know that everybody watching has access to that tool. Salim, nice to see Keith with a beard this time. Yes, I know, showing my age here. All right, so let's go ahead and start with a basic premise of what is spanning tree and why is it needed? Why did it come out? What problem did it solve? And whenever I'm teaching a class, I like to introduce any new concept by answering that question. If you understand what the problem was in networking that this feature was designed to solve, it hopefully solidifies it in your mind as to why you would use it and why it works this particular way. So that being the case, so take yourself back to like the late 1970s. Now, some of you guys may not even have been born at that point in time, but so we're going back now beyond the days of switches. This is the back in the days when bridges were prevalent. Okay, so if you remember your history of Ethernet, when Ethernet first came out, you had just one big long cable that all these mainframe computers would tap into. And then in order to get additional distance on that cable and additional devices connected to it, hubs came out. And then after hubs, bridges came out. So that's where we are right now. We're in the world of devices, mainframes, and some real simple PCs connecting to bridges. Now, how did a bridge work? A bridge was a very simple device. An Ethernet frame would come in a port. The bridge would simply look at the destination MAC address of that Ethernet frame. The bridge would go into its own local bridging table, which was a listing of MAC addresses. It would try to find a match for that MAC address. And if it did find a match, that MAC address in its table also had a corresponding port number where that MAC address lived, where it resided. So the frame would come in and then would go out that particular port based on the MAC address table. But there were times when a frame would come in and a lookup would happen in the MAC address table and there'd be no match, there'd be nothing there, either because that destination MAC address was just unknown, the bridge had never heard from it before, or maybe that destination MAC address was a broadcast. It was intentionally meant to go to everyone, not just one device. So in both of those situations, the bridge would go into its table and say, hey, I don't see a match here for this, so I guess what I'll do is I'll just flood this frame. It came in one port, and I'll just make copies of it and send it out all the other ports. So that was sort of the idea of, when a frame comes into a bridge, how do we get it to the destination if we don't know where the destination is? Real simple, send it everywhere. So that was the idea behind that. But this way of doing bridging had some downsides to it. And so imagine this topology that I've got right here. Now I've drawn two switches, switch 1 and switch 2, but the idea is exactly the same whether we're talking about a bridge or a switch. When it comes to forwarding an Ethernet frame, the concept is the same, whether it's a bridge or a switch. Frame comes in, look up the MAC address, send it on its way. So here I have two devices, we'll just call them two switches. Now the problem came in when, number one, I decide to have redundant links. I would say, hey, one link between these two switches or between these two bridges is not enough. I have so much data, so much information going back and forth that one link is getting overloaded. It can't handle all that data. So I decide, well, I'm going to give myself a second link or maybe a third link to increase my bandwidth, increase my capacity. Well, here is a problem that was introduced by this, and this is the problem that Spanning Tree was designed to solve. So I'm going to go ahead and maximize this so you can see it a little bit better. So imagine that PCA sends some sort of Ethernet frame and the destination is a broadcast. Now there's a lot of types of Ethernet frames that could be a broadcast. It could be a DHCP discover, it could be an ARP request, a lot of different things. But the point is, when switch 1 goes into his MAC address table to look up the destination of this frame, he's not going to find a match. Because a broadcast MAC address, if you remember, always takes the form of just a whole bunch of Fs, right? FF, FF, FF. So that is a broadcast MAC address, or in binary, just a bunch of binary ones. And that is only seen in a destination. It's never seen as a source MAC address, which means this will never show up in the MAC address table. So here comes into switch 1 a broadcast, and switch 1 says, well, since it's not on my table, I guess I'll flood it. So he takes a copy of the frame and sends it out port 2, and he takes another copy and sends it out port 3. Now at the same time, he does some learning right here. In other words, he says, hey, maybe this is the first time I've ever seen a frame from the source MAC address of AA. So I now know that AA exists, and his frame came in on port number 1. So I'll go into my MAC address table, and that's where I will learn him right there. All right, now he sends out these 2 frames here to switch 2. Now, we don't know which of these frames is going to be processed first by switch 2, the one that came in on port 4 or the one that came in on port 5, but that's really kind of irrelevant. Let's just pick one at random. Let's say that switch 2 decides to process the one that came in on port 4 first. So it says, hey, here's a frame with a source MAC address of AA. I've never seen that before. And I'm going to learn it. I'm going to associate it to port 4 because that's where it came in. Now he takes a look at the destination MAC address of that frame. He says, oh, the destination MAC address is a broadcast. I don't have that in my table, so I'm going to flood it. So he takes that frame and he floods it out port number 6, and he also floods it out port number 5. Now a split second later, now he's going to process the frame that came in on port number 5, because that's been waiting to be looked up. He says, oh, hey, this frame that came in on port number 5 is also from AA. So I guess AA has moved. He's no longer on port number 4. I will delete that entry and I will rewrite it as being learned on port number 5. Okay, now hold that thought for just a second. That has just happened. That process of learning AA on port 4 and then deleting it and rewriting it on port 5, that has happened in like a split second. Super, super fast. Now, let's look at switch number 1. Switch number 1 here is now getting a frame coming in on port number 3. Switch number 1 says, ah, interesting. This frame coming in on port number 3 has a source MAC address of AA. I guess he's no longer on port number 1. He must now be on port number 3. And guess what? That's a broadcast. So I'm going to go ahead and flood that. So he sends a copy of that frame to the PC. He also sends a copy of the frame out port number 2. Now it comes in on switch 2. Switch 2 says, oh, here's good old AA again, but he's coming in on port number 4, so I'm going to delete that, and I'm going to relearn it on port number 4, and oh, that's a broadcast frame right here, so I'm going to go ahead and flood that here, and you can see what's happening. At this point, this broadcast is just circling and circling and circling between here. Both these PCs are getting multiple copies of it. Now imagine for just a second. Remember, if these links are, let's say, fast Ethernet links, which means they're capable of 100 million bits per second, okay? And the forwarding engines in these switches, the actual ASICs are responsible for taking a frame, looking it up, forwarding it out. They can do that process millions or tens or hundreds of millions of times per second. So in 1 second of time, how frequently do you think this broadcast frame is being hit by A, and hitting B, and not only that, but when a broadcast comes into a switch, the switch's own CPU has to look at that broadcast. Because after all, maybe somebody is trying to ARP for the switch itself. Maybe somebody's trying to talk directly to the switch. So the switch's CPU also has to pay attention to that. So in this case here, we have 4 devices, the 2 PCs and the 2 switches, and their CPUs are just getting pounded with bam, 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 just like thousands of broadcasts every second. They're just slamming those CPUs. Well, the CPUs of these devices were never meant to handle that onslaught of incoming broadcasts. So from PC A and PC B, probably what you'll see on the PC is your networking connectivity will just stop. You're like, I was in the middle of watching some YouTube video and it just froze. And I can't download my emails anymore and I can't do anything. And my PC is, even when I open up Microsoft Word or Microsoft Excel, it's like it's crawling and my mouse is crawling across the screen. Well, that's because the CPU in your laptop is just dying because it's being pounded with these broadcasts that are coming in. many of which are your own broadcasts, which keep coming back to you. And the switches are having an even bigger problem, because not only are they also having to process this onslaught of incoming broadcasts that they themselves are generating and circling around, but they're having to go into their MAC address tables and constantly erase, rewrite, erase, rewrite. That process also takes a hit on the CPU. So on the switches, what you would probably notice is the CPU getting higher and higher and higher and higher, and eventually you try to log into the switch, you get nothing. You can't even if you're consoled into the switch, you have no access to the command line, it is frozen. And then probably a few seconds later, the switch just crashes. The CPU gets overwhelmed and just dies and crashes, comes back up. So this is what we call a bridging loop. And so, if you were just a regular user of this network, what the indicator would be to you that there's a bridging loop going on is, you're doing your stuff in networking, you're doing your emails, your web browsing, and all of a sudden it's getting slower and slower and slower. And then there's a period of time when you have no networking connectivity whatsoever. That's the period of time those switches have crashed and are reloading. And then when the switches come back up and their tables are empty, network is just fine. But the next time a broadcast goes out, and guarantee there will be one within the next minute or so, now the network's going to get slower and slower. So you got this repeating pattern of the network getting slower, no connectivity, network's fine, slower, 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 no connectivity, network's fine. And that's what you would know as, oh, okay, there's a broadcast storm going on, there's a bridging loop. So this is the problem that Spanning Tree was designed to solve. So, very smart lady called Radia Perlman, who I believe worked at Digital Equipment Corporation, which doesn't exist anymore. Like I said, this is back in the late 1970s, early 1980s, I believe, came up with a solution to this. She said, okay, well, the whole reason why we have this problem is because we have this redundant link right here. So technically, what I could do is just remove that cable right there. No redundancy, I'm done, right? No problem. I don't have a bridging loop. But now what happens if this link goes down? I've got nothing. So she thought, what would be a good idea is if I had some protocol that ran in the background that recognized redundancy in a network and stripped out that redundancy. In other words, it basically made a link useless. It didn't bring it down. The link was still physically up. It still was electrically alive. But this protocol would say, right now, I'm not going to allow any data across this link, because if I do, that could cause a bridging loop, a spanning tree loop. But what this protocol would be smart enough to realize is, hey, if another link does go down, I need to account for that and take my link which was previously down and bring it back up again. So this is what Spanning Tree does. And the reason they call it Spanning Tree, if I'll go to this picture right here. So here's our original tree-like structure. Imagine that each one of these red boxes represents a bridge or a switch. The lines between them are, Ethernet cables are connecting them together. And we have a lot of redundancy here, right? The switch on my floor has connectivity to other switches on my floor, connectivity to switches above me, switches in the basement, and everything's interconnected together. Now this topology right here is ripe for a bridging loop. So when you implement Spanning Tree on this, Spanning Tree says, okay, well, I'm going to start removing some redundant links. I'm not going to take them out. I'm just going to make sure that data is not allowed to flow across those links. And what you'll end up having is, after Spanning Tree is done doing its job, you'll end up with something that looks like a tree, where from any one point to another point on the network, between any two PCs, between any PC and a server, there is only one possible path. All the redundancy has been trimmed off. But Spanning Tree is smart, because if a switch in my tree fails, or if a current active link fails, Spanning Tree can take one of those other links that's currently what we call blocked, it's blocking traffic, and turn it into a forwarding link, where it's allowed to forward traffic to make up for the fact that something over here has gone down or has failed. So that is the idea behind Spanning Tree, why it was developed, and what the concept is. So let me pause here for just a second. Does anybody have any questions on what I've described so far? And let me just take a look through some of the existing questions and see if there's anything I can answer before we start going into the details of how this works. I'm just going to scroll up here a little bit. Oh, hey, David, congratulations on passing your CCNA. That's fantastic. Good job. Salim, you have your ICND 2 in the next 2 weeks. Okay, that's where you're going to be hit with your spanning tree questions. Spanning tree that's where it is introduced in the ICND 2 exam. Okay, so I don't see any questions so far. So let's go ahead and talk about how this happens. How does it come up with this tree? So the way I like to describe is I like to say, okay, if you think about a tree, everything from a tree starts at the roots, right? If you don't have any roots spreading underneath the ground, you have no tree. So a tree requires roots, and then everything sort of branches out from the roots. And as the sunlight comes in, that's converted into energy, which goes down into the roots. You know, the water comes in, goes down to the roots. So just like a tree needs roots to exist, spanning tree needs roots as well. So the roots we're talking about here in spanning tree is one particular switch or bridge is going to be elected to a special role called a root bridge. And I'm going to talk about who is that in just a second. How do we determine that? But once all the switches know in the topology, oh, that guy over there, he's the root bridge, then the tree is formed based on where he is. And the shortest path to reach him, everything about this tree is based on the root bridge. Now you might be asking, okay, well, what if I have a root bridge and my tree has been formed and my root bridge goes away? Like someone yanks him out of the topology, or it just crashes and dies? Well, guess what? Like so many networking protocols out there, right? A lot of networking protocols make use of hellos or keep alives, where some device says, I'm here, I'm here, I'm here, over and over and over again. As long as it keeps doing that, the protocol is stable, everything's good. It's when those hellos or keep alives stop that the protocol scrambles and says, okay, I need to account for this, I need to do something. Same thing is true with spanning tree. This root bridge that we're going to see here in just a second has to periodically send out these hello messages saying, hello, I'm here, I'm still the root bridge. And if he stops because he crashes and dies or something like that, then after a certain period of time, all the switches will elect a new root bridge, and a new tree will be formed based on the location of wherever that new root bridge is. So when you're taking a look at a topology of switches, so let me go ahead and get rid of this right here. So let's go into Packet Tracer now. So let's just make a simple topology of, let's say, 4 or 5 switches. Let me make this a little bit bigger here. So it doesn't really matter which switch I select from Packet Tracer. I'm just going to select the 3560s. Let's just put one right there, one right here. Let's just do a simple triangle to begin with. All right, so I've got 3 3560s. Now I have not connected them yet, but once I do connect them, they're going to start running spanning tree. And this is also another thing for the Cisco certification exams, is spanning tree is not something you have to turn on. It's already on by default. So everything I'm about to show you is happening in the background. Now there's certainly ways to influence spanning tree and make it do what you want it to do, but you can just leave it alone and it will do all of this. It will do its loop prevention all by itself, which is the great thing. Okay, so let's go ahead and connect these guys together. Because we're talking switch-to-switch connectivity, we need a crossover cable. So if you just hover over the cable types down below, if you haven't done this before, and you look way down here in this section, so if you look down here as I'm hovering over the cables, you'll see that it actually indicates what the cable type is. So that blue cable there is console, copper straight through, copper crossover. All right, so let's just select copper crossover. And between this guy here, I'll select fast Ethernet 01. I'll have him go to fast Ethernet 01 over here. And on the same switch here, let's do another crossover cable. But this time I'm going to select his gig port, gig 01, and I'll have it go to gig 01 on this guy. And one more. Let's do fast Ethernet 02 going to fast Ethernet 02. All right, and so we can see this. I go to options, preferences. I'm going to put on here because we're going to put show port labels. Because in spanning tree, it's very important that you know what the actual port number is. Is it 01? Is it 08? You actually have to know that in order to decipher topology. So when I talk about deciphering spanning tree topologies, what I'm really talking about is looking at a topology like this and being able to figure out what the tree is going to look like. What link is not going to be used because it's going to be blocking somewhere. All right, so and that's our ultimate end goal. Which of these three links is not going to be used by data? So let's just put a couple of PCs in here. Put one right there. And let's put one right here. And let's just put one right here. All right, and we'll connect those guys up with some straight-through cables. So our ultimate objective here is to figure out when these PCs are talking to each other, what the path is that their Ethernet frames are going to take. What's going to be blocked by spanning tree. Okay. Now, packet tracer actually shows it to us. So, you know, if we were lazy, we could just look at this, and I'm not sure if you're familiar with this or not, but in packet tracer, if everything is just on one VLAN, and by default, everything's on VLAN 1 here, the green light means it's in the forwarding state. It is wide open for sending and receiving traffic. This sort of orange dot means it's blocking. So we can see that this one is blocking. Now the question is, why is that blocking? All right, so let's go through the logic here. So step number one of spanning trees, we have to figure out which switch is going to be our root bridge. Everything is going to branch off from the root. So how do we do that? Well, in the world of spanning tree, when a switch first gets turned on or enters the topology, it doesn't know who the root bridge is. So that switch starts sending out these special spanning tree hello messages, and BC2 man beast, yeah, you got it, it's called a BPDU. So the name of this message is called a Bridge Protocol Data Unit. BPDU. And this is the message that goes out by spanning tree. This is the fundamental building block where everything learns of the topology and ultimately decides what's going to be forwarding, what's not going to be forwarding, what's going to be blocking. So inside that BPDU, there are a lot of different fields. I'm not going to get them in order. You don't, you know, for any certification test, you should know what the fields are and what their purposes are, but you don't necessarily have to get them in the correct order. So I'll start out with one of those fields is called the root bridge ID field. Another field is called the sending bridge ID. So this first box here in the BPDU says, here is who I believe the identifier is of the root bridge, the name of the root bridge. And the second box says, hey, I'm sending this BPDU to you. It's coming from me. So I'm going to put my own name in the sending bridge field. Now imagine that all three of these switches got powered on at exactly the same time. So they have to elect a root bridge. So at the very beginning, because a switch doesn't know what the topology is, it doesn't know if there's an existing root bridge or not, it takes its own name and puts it inside the root bridge ID field. It says, well, I'll just assume that I'm the root bridge. Until somebody tells me better, I'll take over that job. Now, what does this bridge ID field look like? Well, you know, it's a number, right? But as a number, it's actually divided into two separate components. See if I can fit them in here. So if we were actually looking at it, so if we're saying that this field is, this Ethernet frame is going from left to right. So let's just say then that this field here on the right, this would be the first field that you would read. That is the bridge priority. So every bridge has a number of a bridge priority. And then after that, there's the bridge MAC address. Okay? So the bridge ID is composed of two subfields, a bridge priority and a bridge MAC address. Now, for the purpose of any certification exam, you need to know what is the default value for the bridge priority. I'll give you a little bit of history lesson for this. So Radia Perlman, when she developed this and she developed the structure of this BPDU, she said, okay, well, the bridge priority, I'm going to make that 16 bits. So 16 bits long. So if you think about a number, so if you think about 16 bits, okay? So if I was to draw out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Or if this was my priority field right here, 16 bits long. The absolute lowest number you could have would be all zeros. I'm not going to fill it all in here, but you know, a priority of 0 would be the lowest number. What's the highest number you could have? All ones, right? And if I fill this in with all ones, that would be 65,535. So Ms. Perlman decided, well, I'm going to make the default bridge priority be right in the middle, half of that. So between 0 and 65,535, she decided that the default bridge priority would be 32,768. And yes, for a certification exam from CCNA all the way to CCIE, you will want to memorize that number. Now, through iOS commands, you can change that. And a lot of people do. You can change that number, but that is the default, 32,768. Now, the MAC address, you can't really predict in advance what that's going to be. On some switches, there are some show commands where even if the switch isn't connected to anything, if there were no cables, you still might be able to predict what MAC address it would use. But I'm just going to put in some random MAC address here. All right, so let's just say that's the MAC address. So the bridge ID is this total combined number, 32,768 or whatever the priority is, and the 48-bit MAC address following that. So that whole thing together is considered the bridge ID. So you got a switch now, or a bridge, that's taking his name, which is his sending bridge ID, and he's copying it into this field called the root bridge ID. But we can only have one. We can only have one root bridge. So imagine all these switches are exchanging BPDUs. Who's going to win? In spanning tree, whenever you're comparing two values against each other and you're trying to determine what's the winner, what's the best, lower is better. Whatever the lower the number is, whatever the lower value is, that is the winner. So if we go back to my topology right here, we need to figure out, of these three switches, what their bridge IDs are, and whoever's got the lowest bridge ID, that will be our root bridge. Now, if all the switches or bridges have the exact same priority, and they will by default, every single one of them will be 32,768. Then it will default to whoever has the lowest MAC address. That will be our winner. That'll be our root bridge. When kind of a funny, interesting little factoid here is that if I have an environment of new switches and old switches, guess what switch is going to be my root bridge by default? My oldest switch, whatever switch was manufactured the earliest, because a switch that was produced and manufactured in 1999 is going to have a lower MAC address than a brand new switch that was manufactured yesterday, right? Because companies get batches of MAC addresses and typically they take the lowest one and they just go up from there. So your really old, outdated switch, that's going to be your root bridge. Now you probably don't want that. You probably, maybe that switch is like in some far, dusty corner of the network somewhere. You want, ideally, a switch that's pretty much right in the middle of your network, in the core layer of your network. You want that one to be the root bridge. And also you want a switch that's like a big, beefy core or distribution layer switch. You don't want some small, puny little access layer switch being your root bridge. So if there's nothing else that people do with spanning tree, is they will identify, okay, that bridge right there, I want that one to be my root bridge. How do you make that happen? You change the priority. And there's actually a couple of different ways you can do that in Cisco iOS. I'll go on to, actually let's just take a look at Packet Tracer. First of all, what options does Packet Tracer give us? So if I go into the command line here, make this a little bit larger. Now on Cisco switches, I'm assuming that if you're watching me right now, you are familiar with the concept of VLAN. So I'm not going to go into what a VLAN is. On Cisco switches, each VLAN that's active, in other words, a VLAN has at least one physical interface in it. That's what makes it active. Each VLAN that's active is running spanning tree. So if I have 5 VLANs in my switch, VLANs 1 through 5, VLAN 1 is running spanning tree. That VLAN has some root bridge somewhere, and it's formed a tree for VLAN 1. VLAN 2, it's got a root bridge, and there's another tree for that one. So all of your spanning tree commands in Cisco switches, you have to include the VLAN that you're concerned about. Which tree do I want to look at? The one for VLAN 2, the one for VLAN 19? So this is called per VLAN spanning tree. So if you see that acronym PVST, that's what we're talking about here. Each VLAN doing its own separate spanning tree. Now I haven't configured any VLANs in these switches, so I should just have VLAN 1 pretty much. So for my show command, actually I'm not going to do a show command. I'm going to show you the command to, first of all, set the priority of a switch. So it would be spanning dash tree VLAN, select your VLAN number, and then to change the priority, okay, good, it does have both commands here. You can manually set the priority, spanning dash tree VLAN 1 priority, and then set some number as your priority. So for example, if I wanted this switch here to be the root bridge, I could actually give it a priority of 0. And once again, assuming there's no other switch that has the same priority of 0, this guy will be the winner. Now, if there is another switch in this VLAN that also has a priority of 0, guess who's going to win? Whoever's got the lowest MAC address. That will be my root bridge. But I'm trying to avoid the MAC address being the winner. I'm trying to make the priority dictate who's going to win by being the lowest priority. Another very popular command that people like is spanning tree VLAN, whatever the VLAN is, root primary. Root primary. And what that command does is as soon as you hit enter on that command, the switch will take a look at its spanning tree table and say, okay, is there a current root bridge out there who's not me? Let's say there's a root bridge out there right now whose priority is 8,192. So my switch, where I just did the root primary command, will say, okay, well, I want to beat him, so I need to have a lower priority than 8,192. And it'll actually automatically lower the priority low enough to beat that guy. Now there's more logic to it than that as far as like how does it pick a number. Once again, I'm sort of on constrained time right now, so I don't really have time to talk about extended system IDs and things like that. But the main thing I want to reinforce right now is the default priority is 32,768. If we want to make one particular switch the root bridge, the way you do that is you knock the priority down. And you can either do that manually with the spanning dash tree priority command and set your number, or you can do it with the spanning dash tree VLAN root primary command, and that will automatically pick a number for you, which will make it the root bridge. Now there is one caveat though with this command right here, with the root primary command. Let's say that I currently have a root bridge. Let's say right here, this is my root bridge, and he is the root bridge because he is 4,096. That is his current priority, and then he's got some MAC address right here. Well, the spanning tree VLAN root primary command will not work on any other switch to beat this guy. Why not? Well, when this command takes effect and says, I need to lower my priority, it actually lowers it in multiples of 4,096. So for example, if this guy was the current root bridge because he was 8,192, no problem. If I did the command right here, he would end up having a priority of 4,096. He would say, okay, I need to be lower than 8,192. What's the next increment down? What's the next 4,096 value less than that I can select? Oh, 4,096. Okay. But if a switch is already 4,096, you might think, oh, well then why doesn't this command just knock him down to 0? It doesn't do it. It just won't do that. So if the current root bridge is 4,096, the only way to make this guy the root is by actually using the other command that I showed you, which was the spanning dash tree VLAN, and then actually set the priority to 0. If you want a priority of 0, you can't do that with the root primary command. You can only do that manually with the spanning tree VLAN priority value. So that's just one little caveat about that. Okay, so that's how you deterministically set the root bridges, by going on to whatever, not the root, so we can compare and contrast that. Let's go to this guy over here. All right, same command, show spanning dash tree VLAN 1. Let's zoom in here a little bit. Okay, so we can see that this is the information about my local switch. You can see he's using the default priority of 32768. Now, Cisco switches for decades have done something called extended system IDs. And what an extended system ID is, simply means it takes the priority and adds the VLAN to it, and that's what gives the total priority. So that's why it says 32769. If I had done this for VLAN 10, it'd be 32778. 32768 plus VLAN 10, which would have been 32778. So that's what's called an extended system ID. So here we can see, this is my MAC and priority, and this right here is the priority and MAC of the root bridge. So the root bridge beat me. He's the winner, not because of his priority. His priority is the exact same, but because of his MAC address. Because if we just start comparing the MAC addresses from left to right, 0 and 0, 0 and 0, oh, here we have some differentiation, 0 here and 3 right here. And once again, lower is better, so 0 is lower than 3, so this MAC address is better or lower than this MAC address. So that's why this switch became the root bridge, simply by virtue of having the lowest MAC address of all the switches. So if you're ever given a spanning tree topology, like a diagram, such as something like, let's get rid of this, we don't need this anymore, something like this, and you're asked to figure out what's forwarding, what's blocking, what's this topology going to look like, first thing you have to ask yourself is, what is my root bridge? And in order to answer that question, you need to know what the bridge ID is of every single switch. And remember, you have to look at the priority first and ask yourself, do any of these switches have a lower priority than any other switch? If they do, you're done. Whoever has the lowest priority, that's the winner. If the priorities are all the same, or if there happens to be a tie in the priority, then it's whoever has the lowest MAC address. And you just parse the MAC address from left to right. You just start comparing the numbers. Okay, 0, 0, 0, 0, 1E, F, C. Oh, C is lower than FD. Okay, between these two, that guy's the winner. And so you go through this, and that's how you would figure out who your root bridge is. So that's step number 1, is identifying the root bridge, either on paper, by looking at the MAC addresses and the priorities, or by actually going into a device and issuing the show spanning dash tree selective VLAN. And then remember, this part right here is your own local information. Okay. Now you might think, oh, well, why do I, in this case, it clearly tells me who the root bridge is. Why do I care? Well, imagine that my picture looked like this. Hold on a second here. Let me just do a new one. Okay, imagine my picture was like this. Let's say I had a switch right here, had some laptops connected to it. So these are some laptops here. Some laptops connected to this. So these are 2 real switches. Imagine these are 2 physical switches. Switch 1, switch 2. Okay. All these laptops are in the same VLAN. I don't know what it is. Let's say VLAN 7. And you have to identify, okay, before I connect switch 1 and switch 2 together, before I connect a cable, I want to predict in advance which one of these switches is going to be my root bridge. Well, if you log onto them right now, they will both say they're the root bridge, because switch 1 will say, hey, I'm the only bridge here. In VLAN 7, it's just me. I'm the root bridge. And guess what? If you log on to switch 2, he's going to say the same thing. He's going to say, I'm the only switch in VLAN 7. I haven't gotten BPDUs from anybody else. I'm the root bridge. So issuing the show spanning -tree root command right now on these two switches and looking at the top part, this part right here, won't help you because they're both going to say they're the root bridge. That's why you'd have to say, all right, I need to look at the bottom part here and I need to identify what the bridge ID is of switch 1 and switch 2 and then figure out which is lower, which is going to be my root bridge. So that's step number 1, identifying the root bridge. And then once you've identified that root bridge, like in this particular case right here, we know that all the ports on that root bridge for that VLAN, because remember, we're just concerned with this particular broadcast domain, this VLAN, are going to be in the forwarding state. Now, what does forwarding mean? In terms of spanning tree, we have things called an interface that's participating in spanning tree, right? An interface that's either sending or receiving BPDUs is going to have a certain port role and a port state. So let's go back to my whiteboard here for a second. So in spanning tree, each interface has a, so I'll start out with port role, and over here we'll say port state. So the port role, the way I like to describe that is what is the job / responsibility of this interface as it pertains to the STP protocol. Okay. Is the job of this port to put BPDUs on the wire every so often? Is the job of this port just to be listening for BPDUs? You know, what's it doing as far as the protocol is concerned? And the port state is this port allowed to send and receive user data? That's the port state. So the first port role we're going to talk about, which is tied into the root bridge, is a port role called a designated port. So the definition of a designated port is, on any given cable, the port that is closest, and I'll define what closest means, the port is closest to the root bridge is the DP. Its job is to periodically transmit BPDUs onto the cable. Okay, so that is the role of a designated port. It's the port that's closest to the root bridge. So if I go back to this, we already know the switch on the top is the root bridge. So clearly on this cable, you can't get any closer to the root bridge than being on the root bridge. So on this cable right here, this is going to be a designated port, this is going to be a designated port, and this is going to be a designated port. Every single interface on the root bridge will be a designated port because you can't get any closer than being physically on the root bridge. And so that means that every so often, it's going to be his job to transmit BPDUs onto that cable. Now, for the purposes of the CCIE exam on up, you should also know the frequency. How often does the root bridge put those BPDUs onto the cable? And that frequency is every 2 seconds. Every 2 seconds, BPDUs are put onto the cable. All right, so that's the job or responsibility of a designated port. So that's the port role. What about the port state? Well, a designated port is always in the forwarding state, which means wide open to send, receive user data. All right, so a designated port is always in the forwarding state. So that's why, given this particular topology right here, I would mark all these ports as DPs, and I put like a little F next to them. All right, so in order to decipher this topology, step number 1, figure out who your root bridge is going to be. Step number 2, go to all the ports on that root bridge, mark them as designated ports, and forwarding. So I'm going to take a break here and take a look and see if you guys have any questions that I haven't answered yet, and then we'll keep moving on with this. Okay, how does spanning tree block a redundant path? We're going to get there. That's actually going to be the last thing we're going to do, is figure out what ends up blocking. Internetwork Training asks a question: how can you explain the proposal and agreement in spanning tree? So proposals and agreements, what we're talking about today, so Radia Perlman came up with the original spanning tree. She gave it to the IEEE, and they made a specification out of it. That specification is what we're talking about today. So the original spanning tree from the IEEE was 802.1D, 802.1 David. That's what we're talking about today. Several years after that, they made some updates to it, and they came out with 802.1W, and that is rapid spanning tree, and that's where proposals and agreements come into play. In 30 seconds or less, I'll just tell you what those are. So you and I are two bridges, or you and I are two switches. We connect a cable between us. In 802.1D, even though it's just you and I on this cable, it's going to take a little bit of time before we finally figure out, are you going to be forwarding? Am I going to be forwarding? Are you going to be blocking? Am I going to be blocking? You know, what's the port role going to be for you and for me? That's going to take anywhere from 30 to 50 seconds, depending on things, before we finally decide what we're going to be. In rapid spanning tree, when this cable comes up, as we exchange BPDUs, we actually flip a couple of bits in there called proposals and agreements. And so with just a quick rapid fire exchange of BPDUs that takes place in like a second or two, we know ultimately what our port role is going to be. With just a 1-2 exchange of BPDUs, for example, I might know that I'm going to be a designated port, I'm going to be forwarding. You might realize that you're going to be blocking, or you're going to be something else. In 802.1D, even though we exchange BPDUs, and we might know that, we'd still have to wait 30 to 50 seconds because, hey, there might be somebody else on this cable that just hasn't sent a BPDU yet. We need to wait for them. In rapid spanning tree, we say, hey, this is a point-to-point cable. This is full duplex here. There can't be anybody but us. There's no third party we're waiting for. So in rapid spanning tree, when we identify as full duplex, now with just a 1-2 exchange of BPDUs, we know I'm going to be forwarding, designated, you're going to be blocking. So in like 2 seconds, we're done. We don't have to wait an additional amount of time in case a third or a fourth switch decides to make a surprise appearance on this cable. We know full duplex, there's only the two of us, so we can use some special bits within the BPDUs to say, hey, let's just real quickly here decide what we're going to be, and then that is it. So that's why they call it rapid spanning tree. What else here? Yeah, so the name of the lady, I might get her name misspelled, but I believe it was, so I just put it there. I think it was Radia Perlman. Not sure if I spelled her last name correctly. But you can Google her. She's got all sorts of books on stuff. And yeah, we haven't talked about cost yet. We're going to get to that. How much overhead or bandwidth or packet size is STP normally claiming on a given link? Is STP greedy? Not really. These BPUs are quite small. As a matter of fact, let's just take a look here in Packet Tracer. One of the nice things about Packet Tracer is got sort of like a primitive packet sniffing tool like Wireshark. It's not Wireshark, but it's something like that built in. So in Packet Tracer here in the right corner, I can click on the simulation pane. Under Edit Filters, actually I can just click on Show None, and then under Edit Filters here, I can select, okay, all I want is miscellaneous, and I want STP. That'll show me BPDUs. And once I start collecting BPDUs, it should show me their size. Okay, so we see they go out every 2 seconds, so I don't have to wait very long. So I'll just stop it right now. Let's select one of these BPDUs here. And does it tell us how big this guy is? Let's see. Well, this doesn't give us the total here. It does show us the size in bytes of each sort of row, but you would have to add these up. But you can see it's not that big. If you just do a quick Google search, you'll be able to see what the total size is of an, make sure you type in 802.1d BPDU, because there are other flavors of spanning tree where the sizes of BPDUs are different. But a BPDU only goes out every 2 seconds. It's not very big, so no, it does not consume a lot of bandwidth or overhead on the switch. And so there's a question, when there's a conflict between two switches, believing they're both the root for one VLAN, how do other VLAN packets get flooded? Well, so there should never be a conflict. Every switch should have a unique bridge ID, right? So in theory, every networking device, every switch, every bridge, every router, every NIC card has its own unique MAC address. So in theory, you should never see two devices that have the same MAC address. Now, that's in theory. Every once in a while in the past, there have been stories about vendors who accidentally shipped out a bunch of NIC cards with the exact same duplicated MAC addresses, but it's highly, highly unlikely that in your environment, you will have two switches that have the exact same MAC address. So, given that, there will always be a tiebreaker. If the switches are talking to each other, then that's the key thing. If they're talking to each other, if they're able to exchange BPDUs, they will recognize that they have different MAC addresses, and whoever has the lowest MAC address will be the winner. So there should not be a tie. The only time I've seen when I get on like 2 or 3 switches and they all say, I'm the root, I'm the root, I'm the root, that's because there's some disconnectivity. Their switches are somehow not able to transmit or receive BPDUs to each other, so they don't know that the other switch even exists. And so you'd have to troubleshoot that. Why are the BPDUs not making it between the two switches? But if the BPDUs are flowing, if you don't have any corrupt links or links with errors or something like that, you should not have a tie. There should always be somebody who wins. And there is no RFC for spanning trees. So RFCs are typically for like layer 3 and above protocols. Spanning tree is a layer 2 protocol. So you would do a Google search on IEEE 802.1d. So 802.1d is the IEEE specification that we're talking about today. Topology change notifications, we're not going to have time, unfortunately, to get into that. I just have time to show you the topology and how to figure that out. That'll have to be a topic for another day. All right, so let's go back to this. All right, so given, let's see here, maybe I can do this one here. All right, yeah, we can use this. All right, so we want to figure out what our topology is going to be here. Who is going to be our root bridge and everything like that. So first thing, let's go ahead and get rid of some of my redundant links here for just a moment. That'll come in later. Is we have to know what the bridge IDs are. So let me just put some bridge IDs onto this topology, because without that, we're dead in the water. We can't figure it out. So by default, we're all going to be 32.768. I'm just going to put some MAC addresses on here. And as I do this, I want to see if you can figure out what the root bridge is going to be. Okay, so who can tell me in this topology diagram right here, who's going to be my root bridge? Let me just put some numbers. Let's say, is it going to be switch 1, switch 2, switch 3, or switch 4? Well, hopefully you said switch 4, because they all have the same priority, 32768. So if we start reading their MAC addresses from left to right, they all start with 0211. If we go into the next hexadecimal word, they mostly have 34, but this guy down here has 31, and 31 is lower than 34. So now we know what is going to be the port roll. What's going to be the port roll? Remember, here is, it's not that, where is it? Here are port rolls I've talked about so far. Let's give you a quick view of that. So what's going to be the port roll of all of his interfaces? Hopefully you said designated ports. And yes, Endrit, you are correct. All the ports, the port state is going to be forwarding. Okay, so let's just put a little circle around that. So that was part 1. Figure out the root bridge. I should say step 1. Step number 2, every other switch that's not the root bridge has to say, okay, so let's say I'm a switch and I've got lots of interfaces, and I'm getting the root bridges out there somewhere, and I'm getting BPDUs from him on 5 or 6 of my interfaces. Oh, there's one that came in on Fast Ethernet 01. Oh, there's one that came in on Fast Ethernet 07. So I know that I have multiple ways, multiple paths to get back to that root bridge. The next question I have to ask myself is, of all these interfaces that could lead me back to the root bridge, which one is the best? What is the fastest, best path that will get me back to the root bridge? And whichever one that is, like let's say it's this one, Fast Ethernet 0/9, I will mark Fast Ethernet 0/9 as a different kind of a port roll. Let's go back to that. So that port roll will be what's called a root port. Root port. And that is port with lowest cumulative cost. We'll talk about cost here in just one moment. Back to root bridge receives BPDUs from upstream switches. And a root port, just like a designated port, the state of that is always forwarding. Okay, so what do I mean here by cost? So if we take a look at a topology, let's go back to this. For example, let's take the switch number 2 right here. So switch number 2 at the very beginning is going to be receiving BPDUs this way and BPDUs this way. And he has to figure out, okay, which interface is the best one that's going to be my root port? Well, when Radia was determining this protocol, she could have done it based on hop count, like RIP does. You know, how many hops away, how many hops of bridges do I have to go through to get to the root bridge? She didn't do that, so she elected not to do that. She could have done it based on time. Hey, let's have all these switches synchronize their clocks, and then when a BPDU goes out, let's put a little timestamp in there when I get it, see how many microseconds it took me to get it, and she didn't do that. She didn't do it based on time. Instead, what she did is she says, well, every single interface is going to be assigned a value called cost. And cost is directly related to the bandwidth of an interface. Let me put that on here. Cost is derived / related to the interface bandwidth. And remember, in spanning tree, lower is better, which means an interface with a lower cost means it has a higher bandwidth. The faster the speed of an interface, the faster it can go, the lower the cost it's going to be. Now once again, we're talking about 802.1d here. This is all related to that. So there are some cost values that you should memorize. If you actually look in the 802.1d specification, there's about 5 or 6 different bandwidth values, and they say, okay, if the bandwidth of a link is this, this is what the cost should be. And I'll give you the ones that you should memorize. So according to that, a 10 megabit per second Ethernet link, which you probably won't see too many of those anymore, has a cost of 100. A 100 megabits per second fast Ethernet has a cost of 19. A 1 gigabit Ethernet link has a cost of 4. And a 10 gigabit Ethernet link has a cost of 2. So you should definitely memorize those values if you're going to be taking any Cisco certification exam. Now, a logical question you might have is, well, what if I have a link that's something outside of that? For example, what if I'm doing an Ether channel and the total bandwidth of my Ether channel is 300 megs? The 802.1d document, nowhere in there does it give you a formula. It says these are the recommended values, but there's no formula, which means it's pretty much up to each individual vendor to derive a formula for themselves for bandwidths that are outside of this scope right here. So a 300 megabit per second Ether channel on a Cisco switch might come up with a different spanning tree cost than a 300 megabit per second Ethernet channel on a Juniper switch. You don't know, because the specification doesn't say what those should be, but these, it does. So the next part here in figuring our topology is we have to ask ourselves, what is the bandwidth of these links? Now, you probably can't see the colors too well in this diagram, so I'm just going to put fast Ethernet, and this one down here will also be fast Ethernet. Okay, so we identified our root bridge, so step number 2 is to go to every other switch, and it doesn't really necessarily matter what the order is, but I usually start with the switches that are closest to the root bridge and then work my way out from there. And I ask myself, okay, which port's going to be the root port? So for example, when the root bridge sends out a BPDU, and actually I will mark this in my other picture that I drew over here, another field within the BPDU is what's called the cost to the root. So when I forward a BPDU to you, let's say the root bridge was behind me. I got a BPDU from him, I'm forwarding it to you. So in this BPDU I'm forwarding to you, the root bridge ID is his name, his bridge ID. The sending bridge ID is me, because I'm sending it to you. And the cost to the root is, from my perspective, what it costs me to get back to the root bridge. The total cumulative cost, even if he's 7 or 8 bridges away from me, the total cost to get back to him when I add up all the links to get back to him. Now, what if I am the root bridge? What if I'm sending you a BPDU and I am the root bridge? Well, then guess what? The root bridge ID and the sending bridge ID will both be the same, and the cost will be 0, right? Because when I send you a BPDU, I say, hey, my cost to myself is nothing. It's 0. So if we go back to this picture right here, so as the BPDUs go out from the root bridge, I'll draw it this way, and I'll draw it this way. Make this a little bit larger for you. The cost on those will be 0 because they're being transmitted directly from the root bridge. Now, if we look at FFFF, if we look at switch 2, he'll say, okay, I just received a BPU on a fast Ethernet port. As that BPU came in, my neighbor told me that his cost to the root bridge is nothing, is 0. However, that was received on a fast Ethernet port. So to get back to that neighbor is a cost of 19. So my total cumulative cost to get to the root bridge that way is 19. Right, same thing right here. Down on switch 3, he'll say my neighbor told me 0, but it cost me 19 to get to him. So my total cumulative cost will be 19. Now switch 3 is going to forward a BPDU up like this. He's going to say, hey buddy, let me tell you who the root bridge is. Let me tell you my name. I'm the sending bridge ID. And by the way, my cost of the root bridge is 19. Now switch number 2 is going to say, okay, well, he told me his cost is 19, but I received that on a fast Ethernet link. Let me give myself a little bit more room right here. So my total cost on that link is going to be 38. He's going to say, all right, and I'm not getting any BPDUs from this guy. Well, actually, right now, the guy at switch number 1 is initially going to be sending BPU saying, I'm the root, I'm the root. Very soon, switch number 2 is going to say, no, you're not, you lost. But right now, he says, the only way I have to get to the real root bridge is off of these 2 interfaces, and there's clearly a winner here. 19 is lower than 38, which means that the total bandwidth along this path is better, faster, than the total bandwidth along this path. So he says, okay, I will mark that as my root port. So that will be my root port, and that will also be in the forwarding state. Put a little circle around that. Now in just a second I'll talk about, well, what if I have 2 or more paths back to the root bridge and their costs are identical? Then what do I do? And that can absolutely happen, and I'll show you what the tiebreaker is for that in just a second. But for right now, let's just continue along with this. So let me get rid of some of these arrows right here. Let's get rid of this one. Now, FFFF, remember this is the very beginning of the spanning tree topology here. He will now send a BPDU back downstream to his neighbor and say, hey, if you ever need to go through me to get to the root bridge, it's going to cost you 19. Right? Switch number 2 is saying, hey, for me to get to the root bridge, it's 19. And this is a very important point. Let's say once again that I'm a switch and I have behind me multiple ways to get to the root bridge. One particular way is a cost of 100. Another particular way is a cost of 19. Another particular way is a cost of 4. And then I say, oh, well, I need to transmit a BPDU to my neighbor down here. I need to forward a BPDU downstream to my neighbor. And in that BPDU, I need to tell him what my cost is to the root bridge. Am I going to tell you that my cost is 100 or 19? Or should I tell you what my lowest cost is? I'm going to tell you what my lowest cost is. So a lot of times people, when they're first learning about spanning tree and they're trying to figure out topology, they can figure out the root bridge pretty quickly. That's pretty simple. But then when they start thinking about the flow of BPDUs and what the cost values are, they get confused because they'll see a switch right here and they'll say, okay, I know that switch is supposed to be sending a BPDU down this way. But that switch, he's got a cost of 5 to get the root bridge this way, 4, 100, and they get confused. And my point is, if you're going to transmit a BPDU to somebody, you're going to tell them what your lowest cost is to get to the root bridge. All those other potential paths you have are irrelevant. You're going to figure out what your root port is, the lowest cost, and whatever that is, that's what you're going to tell your neighbors. So that's why FFFF right here, he's saying, hey, my cost is 19, because he says, hey, my root port, that's my best path, and that path has a cost of 19. Now, switch number 3 here in the lower left-hand corner, he's going to say, okay, interesting. My neighbor just told me that I can get to the root bridge through him. He told me it's 19. But to reach that neighbor, I have to go across a fast Ethernet link, which is another hop of 19. So that's 38. So now switch number 3 says, okay, clearly my bottom path, which is 19, is lower than 38. So I will select that bottom path as my root port. So he'll say that's going to be my root port, and I will put that into the forwarding state. Which leads me to another very key point. A lot of times people who are brand new to spanning tree will make the faulty assumption that if I have a switch that's directly connected to the root bridge, that direct connection clearly has to be my root port. And remember, it's not based on hop count. It's based on cost. So if I had something like this, okay, and let's say that this switch up here was the root bridge. These links are gig, and this link over here on the right is fast Ethernet. And here we're trying to figure out, from switch 3's perspective, what is he going to use as the root port? Don't be fooled into thinking, oh, well, this link right here, because that's directly connected to the root bridge. It's not based on that. It's based on cost. You have to figure, okay, well, that's a fast Ethernet link, which means it's a cost of 19 to get to the root bridge. But if he takes this path, that's a cost of 4 plus another cost of 4. So taking that, what we would consider roundabout path, is actually the better one. That's going to be a total cost of 8. So this would end up being his root port down here, the port that's not directly connected to the root bridge. It's all based on cost. Now, it just so happens in this topology so far, the ports that are connected to the root bridge end up being our root ports. But I just wanted to emphasize that's not always going to be the case. And then, of course, clearly switch number 1 here, he doesn't have a choice, right? The only path he could potentially take to get to the root bridge is that port right there. And if we think about, okay, so let me ask you, switch number 1 here, whatever this port is, I don't know, let's just say it's gig 0/1. When we do a show spanning tree command on switch number 1, what are we going to see as his cost to the root bridge? Who can tell me? Well, as the BPU comes up this way, his neighbor is going to be telling him, hey, if you go through me, my cost is 19. Because remember, his neighbor is going to say, he's going to give him his best cost, his root port. This guy up top is going to say, okay, well, but to get to my neighbor, it's 4. I have a gigabit link, which is 4. So the switch number 1 will say, well, the total cumulative cost is 4 to get to my neighbor and 19 behind that, so it's 23. Exactly, I see the answers coming in now. Fantastic. So yes, so he'll say 23 is his total cost. So that is step number 2 in deciphering a spanning tree topology. Step number 1 was identifying the root bridge. Step number 2 is going to every other switch and identifying which of their interfaces was going to be a root port and marking down what the cost of that root port was. And it is important that you mark down that cost, because when we get to step number 3, you're going to be referring back to the cost of the root port to figure out these additional links we haven't hit yet. All right, so let me quickly take a look and see if there's any unanswered questions here. Okay, now there was a question earlier about what do I do when my cost is a tie, for example. And there's 2 ways that could be the case. There's 2 possible ties. So let's talk about that. I'll draw 2 different topologies right here. So the topology on the left and a topology on the right. And just for simplicity's sake, let's just assume that all the links are fast Ethernet. They all have a cost of 19. Okay, so let me put some identifiers on here. So in both cases, let's say the switch on the top is our root bridge. Okay, and this switch here, switch 3, I'll just call this guy switch 3 as well. So in both cases, we're trying to figure out for switch 3, which interface is going to be his root port. Is it going to be 0, 1, or is it going to be 0, 2? Let's take the case on the left first. So if we take a look at the flow of the BPDUs, we know that he's going to be getting a BPDU down from the left and from the right. And in both cases, these BPDUs are going to have the same cost. The upstream neighbor is going to say, my cost is 19 to reach the root bridge. So switch number 3 is going to derive his total cost. He's going to say, well, 19, but it costs me an additional 19 to reach you. So he's going to say, all right, well, it costs me 38 to get to the root bridge on that, and 38 to get to the root bridge on that port. That's not going to help me. Both costs are identical. So remember this phrase. Remember the movie from the 1980s, Back to the Future? For those of you who were alive back then, well, remember this phrase, back to the BPDU. Whenever there's a tie, we're going to go back to the BPDU. We're going to compare what's in the BPDUs against each other and try to see if we can find a tiebreaker within the contents of the BPDUs that we've received. So switch 3 in this case, he's going to take a look at these two BPDUs and he's going to say, all right, cost, that didn't help me. So the next thing he does is he goes back to the BPDU and he looks at the sending bridge ID field. And he compares the sending bridge ID field of one BPDU to the other BPDU. So he says, okay, on the left, maybe the sending bridge ID field was 32768, and the MAC address was 02113456, blah, blah, blah. This other one was 32768, and his MAC address was 0211FFEA, blah, blah, blah. So switch 3 says, okay, since the costs were the same, I'm going to take a look at the IDs of those two neighbors. And whichever neighbor has a better name, a better ID, that's the one I'm going to pick. So switch 3 will say, okay, well, 02113 is lower than 0211F. So simply by that virtue, I'm going to mark 01 as my root port. And I'm going to put that in the forwarding state. So that's the first way you do a tiebreaker. If you as a switch have multiple paths to get to the root bridge, and two or more of those paths have the same lowest cost, then you're going to compare the BPDUs that are coming down in those paths, and you're going to look at the sending bridge ID in the BPDUs and try to see is one lower than the other. In the case on the left, it is, and we can make our decision. Now the case on the right, even that's not going to help us. So if we take a look at these BPDUs coming down, so in this particular instance, both BPDUs are going to have the same cost. Cost is going to be 0. So his total cumulative cost will be 19 and 19. That's not going to help us. And then he's going to take a look at the bridge ID, 32768. Dot, 1111, 1111, whatever it is, and he's going to say, okay, those are the same. Both of these BPDUs have the exact same sending bridge ID. Now he's going to go back to the BPDU, and now he's going to look at another field that I haven't drawn yet. I'm going to draw that right in here. So when I send a BPDU to you, when I forward a BPDU to you, I put my own name as the sending bridge ID, and then whatever this port is, whatever this interface is that I'm using to transmit it to you, Spanning Tree has an ID for the port. We call that the sending port ID. And just like my name, my bridge ID is composed of two values, my priority and my MAC, the sending port ID is also composed of two values. Each interface has a port priority. So let's put that right here. Port priority. And then there's the second part of this, which is we simply just call it the port identifier. So the sending port ID field is composed of those two values put together, the port priority and the port ID. Now, just like I said, you need to know what the default value is for the bridge ID, for my overall name. You need to memorize that's 32.768. You should also know what the default port priority is for the port. On the vast majority of Cisco switches, I'll just write this down here, default port priority is 128. I say the vast majority of Cisco switches because if you're actually dealing with a really old Cisco switch that's running the Catalyst operating system, like a Catalyst 5000, they actually had a different port priority. But I'm assuming that most of you probably don't have any of those, so for the purposes of an exam, from the CCNA on up to the CCIE, you should just write down and memorize that the default port priority is 128. Now, what's the port ID? You can't predict that. This is one of those things that the IEEE document, the 802.1d specification, says that when a BPDU is transmitted from an interface, it should have a port priority, and they recommend 128, and it should have a port ID. But nowhere in that document does it say how that port ID section should be derived. So once again, that is different vendor by vendor by vendor. And even within the same vendor, for example, Cisco has lots of different business units, right? All of their switches are not made by the same department. Cisco is so large, they've got like dozens of different business units. One business unit will make the Nexus 5000 switch. Another business unit will make the Catalyst 3560 switch and the 6500 switch. And the business units don't always talk to each other about little details like this. So you'll actually find that the port ID field that's derived in a Catalyst 6500, that number, like for example, Fast Ethernet 01 on a 6500, whatever the port ID is that's derived for that will be completely different than the port ID derived for Fast Ethernet 01 on a Catalyst 3560. Same company, different business units. But here's what I can tell you. If I have, let's go back to this. No, not that. Where is it? This one right here. So if I take a look at my neighbor's ports, and let's say this is 0/4, and this is 0/7, okay? I may not be able to, I know that the port priority will be 128. I know that. That's the default. I can predict that. Now, I don't know and I can't predict what the port ID number will be. But what I do know is that on this one switch, whatever the port ID of 04 is, it will be numerically lower than 07. Let me show you an example of this. I'm going to run a real switch here for this. So this is going to be a 3560 I'm showing you. Let's see what VLANs do exist in this switch. Hold on a second while I get... So you notice how I got this message up here that says spanning tree for VLAN 1 does not exist? That's because none of my interfaces are up right now. They're not connected to anything. So VLAN 1 doesn't have any ports. Now it should. There we go. See, like look at this right here. So notice that Fast Ethernet 021, it has a port priority of 128, but the port ID, otherwise known as number here, is 23. How do they come up with 23 for a port that's Fast Ethernet 021? I don't know. You know, Fast Ethernet 01, how does it have the number 3? I don't know. But what you can tell is if I've got two BPDUs, if I got a BPU coming out of Fast Ethernet 021 and another one coming out of fast Ethernet 024, I won't be able to predict what these numbers are, but I can tell that whatever the number is for 21 is going to be lower than the number for 24. If I had another switch I could jump into, I would show you that those numbers are completely different. So going back to our picture right here, if you had automatically assumed, oh, well, the cost is the same, and my neighbor's bridge ID is the same, so therefore it must be fast Ethernet 01 will be my root port. You would have been wrong, because it's not based on your own interfaces. Your own interfaces have nothing to do with it. Remember, it's back to the BPDU. You got to go back and look in the BPDU, and you have to look at the sending port ID that's in the BPDU. And if both these ports have the same priority, then it's going to be 0/4. Whatever his port ID is for 0/4 will be numerically lower than 0/7. So that will affect the downstream neighbor. So switch 3 in this case will say, this will be my root port. I'm going to put that in the forwarding state, because my upstream neighbor sent me a BPDU with a lower port ID than that same upstream neighbor when he sent me a BPDU on this interface that had a worse port ID. So that's how you deal with a tie. Now, it looks like some questions have come in. Let me take a moment here and see if I can answer any of them. Yeah, how do we calculate cost if we have a port channel between a switch? You really can't predict that in advance. You would just have to take a look at it after it's put up. But if I showed you a topology, if I said, okay, here's a picture, figure out the spanning tree, and if in that link there was an ether channel, you'd have to ask me, because there's no way you could say, oh, I know that ether channel will be a cost of 12 or 5 or 7. You can't predict that, so you'd have to know that in advance. It's all based on the bandwidth. Okay, doesn't look like there's any other questions that have come in so far. So let's go back to this. Let me get rid of some of this stuff right here. So step number 1 in deciphering our topology was identifying the root bridge. Step number 2 was going to every individual switch and identifying the root ports. Step number 3, on every cable between two switches, one of the interfaces on that cable has to be a designated port. Now, why is that? Remember what the job of a designated port is, right? The job of a designated port is to be dumping BPDUs onto that cable every 2 seconds. That's its job. If BPDUs are not put onto that cable, how is the other side of that cable supposed to know what he's supposed to be doing? So every cable has to have somebody who's putting BPDUs onto the cable, and that is the job of the designated port. Now here we've already got a designated port there, so we know BPDUs are going out on the cable that way. We've already got a designated port there, so we know BPDUs are going out that way. But what about these remaining 2 cables? Well, we have to figure out who the designated port is. Let's go back to our definition of the designated port. If I can find it, that is. I'm going to get rid of that. Let's get rid of that. Okay, so remember, the designated port is, on any given cable, the port that is closest to the root bridge, closest via cost, not geography, not distance, cost, is the designated port. So let's go back to our picture right here. All right, so let's take a look at this cable. This switch here, he says, the best cost I can come up with if I want to win, if I want to be the designated port, the best cost I can come up with is my root port over here, which is 19. So I'll tell my neighbor that's the best I can do. The guy down here, he'll say, isn't that funny? Because my root port is also 19. Now, if there had been a clear winner, if one of these guys had obviously had a lower cost to the root bridge than the other one, we would be done. Whoever had the lowest cost, he would take over the job on that cable of being the designated port. Here we have a tie. All right, well, think about the tiebreaker process, right? What was the tiebreaker process? If the cost was the same, the first thing we did as a tiebreaker was we compared names. We compared bridge IDs. So that's what we're going to do here. These two guys are going to look at each other's names. So if we take a look at their names, 34CF, FF1 is lower than FFF. So the switch on the bottom here, he's going to be the winner. His cost is the same, but he's going to say, I'm going to win because my priority is the same as yours, but my MAC address is lower than yours. So he will be the designated bridge on that segment, the designated port, and he will go into the forwarding state. Now, what about this up here? Well, if we just do process of elimination, right? We've already determined that this is the root port, so we're not going to change that. So process of elimination says, hey, a root port receives BPDUs. RP receives. A designated port transmits BPDUs. So clearly this has to be the designated port. But if we just did it, once again, with values, with numbers, start out by comparing costs. Right? This guy here says, hey, my cost to the root bridge is 23. This guy here says, my cost to the root bridge is 19. We're done. He's a winner. The guy on the bottom, 19, is our winner. So this becomes our designated port, and it goes into the forwarding state. Now I'll tell you a little trick. Whenever you have a point-to-point link like this, where there's only two switches on the link, if you've already identified one side as being a root port, you don't have to bother comparing numbers. If one side's a root port, the other side is always a designated port. That's just how it's always going to work out. If you got root port on one side, you're going to have designated port on the other side. So that was step number 3. Step number 1, once again to recap, identify our root bridge. Step number 2, go to every switch that's not the root bridge, identify their root ports. Step number 3, go to every single link and make sure there's a designated port. If there isn't one, figure out which side of that link will be the designated port. And then step number 4, whatever's left is going to be our last port roll. If I can fit that in right here. So we have designated ports, we have root ports, and now we're going to have, if I can fit it in here, non-designated ports. Receives BPDUs. And a non-designated port, his port state is always blocking. Is in the blocking state. So if I go back to this, if we look at our topology here, the only port that we haven't touched yet is this one right here. So that's going to be our non-designated port. I'll say ND, and we'll put a B for blocking right there. Now, one other thing to be aware of when it comes to blocking. A lot of people, when they first start learning about spanning tree, they make the incorrect assumption that when a port goes in the blocking state, nothing is transmitted out of that port. And if anything comes in, dropped, killed. That's not true. Blocking ports are still allowed to transmit control information. For example, they're still allowed to transmit Cisco Discovery Protocol, CDP, goes out of a blocking port. The Dynamic Trunking Protocol for trunking, DTP. The VLAN Trunking Protocol, VTP, all that TP stuff goes out of a blocking port. That can be still transmitted. And if any of that stuff comes in, it is still processed. Blocking is just in reference to user data. So no telnet, no web browsing, no FTP, TFTP, none of that stuff can go out or come in a blocking port. All right, so with that, that is how you decipher a span tree topology. So what I'd like to do now with our remaining few minutes is I would like to give you some topologies and give you like a minute or a minute and a half and see if you can figure them out. I'm going to give it to you like as like a CCIE type question. See if you can figure it out. So let's get rid of this. We won't do that one first. All right, so I'm going to make that bigger. So here you have a multiple choice question. Which ports in this topology will be blocking? Go through the 4 steps that I talked about and see if you can figure out in this multiple choice question which of these answers, if any, will be blocking. I will give you 1 minute to work on this, starting now. Now, when you figure out the answer, don't type it in. Otherwise, you'll spoil the fun for other people. So just keep your answer to yourself. I'll give you 30 more seconds. Okay, so let's go through it together. So this one, hopefully you quickly determine the root bridge as being 4096. That's the lowest priority, so that guy is our root. So we know that all of his ports are going to be in the forwarding state. So right there we can cross 0/2 off the list. That can't possibly be blocking. All right, then we identify our root ports. If I start with the top switch, I think it's pretty clear that 04 will be his root port. Okay, so that's a gig link. So that's going to be a cost of 4. Going the other way will be higher than 4. So this will be forwarding as a root port. All right, if we take a look at this guy right here, well, this is a fast Ethernet link, so that's 19. If he goes up and over, that's 2 hops of gig, which will be a total of 8. 4 plus 4. So this will be his forwarding root port. 06 is not in here. 07 is not an answer, so I don't have to worry about that. If we take a look at this guy right here, 24666, once again, his direct link is a fast Ethernet, which is a cost of 19. If he goes over and around, that's 3 links of gig, 4, 4, and 4, which will be 12. So this will be his root port. Okay? So now we have to identify, so that's step number 2, identifying root ports. Step number 3 is identifying designated ports. So I told you, whenever you got a root port, you know the other side of that's always going to be a designated port. So 08, that is not correct. That will not be blocking. Over here, the other side of a root port, going to be designated. So 05 can't be blocking. Now let's take a look at this, 010. All right, so 010, well, that's not his root port because his root port is over here. That on this wire, that cannot be the designated port because the designated port is directly connected to the root bridge. So by process of elimination, this is our correct answer. Answer C. That was our blocking interface. Let me give you one more like this. I'm going to take this off the screen here for a second so I can make a couple of tweaks to it. All right, so just give me 1 minute here as I make my changes. Just 1 second. All right. Same thing, I'll give you a minute and a half to figure out this one. These dashed lines, in case you couldn't tell before, these dashed lines are the gig links and the solid black lines are fast Ethernet. So you have 90 seconds, try to figure out the answer. You have 30 seconds left. All right, time's up. Go ahead and, before I show you, go ahead and type in your answers. I just want to see how many people came up with something and if there was any variation in your answers. Thank you, Dimitri. Anybody else have an answer besides Dimitri? Don't be shy. Thank you, Tony. Thank you, Krishan. Okay, well, let's go through this. Thank you, Arthur. So hopefully everybody decided that this was our root bridge. They all, so 32,768, 0233, well, that's definitely lower than 0245, so we can rule that guy out. And then among these, ED is lower than EF and certainly lower than F1, so that's our root bridge. So here we have forwarding, designated port, same thing on this, and same thing on this. Okay, so we can rule out 0/8. That's not going to be blocking. Then if we do our root ports, for this guy, this will be his root port because a total cost of 8, 4, and 4 is lower than a total cost of 19. And we know the other side of a root port is always going to be a designated port. Once again, that's if it's a point-to-point link. And on this bottom switch here, let's take the top switch. Okay, so his root port will be 0/5. So we can rule that out. That can't be the correct answer. And then the bottom switch here. Here's where you had to remember, what do we do when we have a tie? Because the bottom switch said, well, I've got 2 links. They both have a total cumulative cost of 4 to get to the root bridge. So once again, we go back to the BPDU. First of all, he looks at the BPDUs he is receiving. He says, okay, is the sending bridge ID different in either one of these BPDUs? The answer is no. The sending bridge ID is the same. What about the sending port IDs? He says, yes, they both have a priority of 128, but the port ID of 08 is lower than the port ID of 011. So I will choose this as my root port. All right, so now we have all of our root ports. Now let's go ahead and figure out, so that's step number 2. Step number 3 is every link has to have a designated port. Well, this one does, these ones do. Okay, there's no designated port over here, so let's figure that out. Remember, so it's going to be a comparison of the cost of this guy and the cost of this guy. This guy's cost to the root bridge. He's going to say, well, the best cost I have is 8, 4 plus 4. That's the best cost I can come up with. This guy here will say, hey, the best cost I have to the root bridge is 4. It says, my cost is 4, my cost is 8, therefore I am the winner. I'll be the designated port, and I'll go forwarding. So C is incorrect. That will be forwarding. So 0/3 will end up being blocking, but that's not one of our answers. What about this link right here? 02 says, I can't be the root port because that's already been determined. On this link, there's already a designated port, so I can't do that. So I guess I have to be blocking. That's my only choice. So A was the correct answer. Now let's do one more of these, and then I'll take any questions that are left, and then we will wrap it up. Now this next one is not going to be multiple choice. This next one you're probably going to want to open up some sort of screen capture tool like Windows snipping tool or something. This is more of a, being able to figure out topology is one thing, but being able to actually utilize spanning tree to predict what path will be taken between any 2 endpoints, that's a much more useful skill. And that's what I want you to do right here. So your question is, what path will Ethernet frames take between PC AA and BB? We know that in this topology, there's only going to be one path that's forwarding all the way through from one point to the other. And once you identify that path, you've answered this question. So what I would recommend that you do is you use some sort of capture tool like Windows snipping tool. I'm going to do that right here. And maybe with Windows snipping tool, just do a screenshot of this real quickly, and then use the pen or something and just mark out what you think the path is going to be. I'm just making that up right there, and then compare my answer with what you come up with. Okay. All right. So that being the case, I'll give you 2 minutes to work on this final question. got 30 more seconds. Okay, so let's work through this one. So they all have the same priority. So we look at our MAC addresses. They all have the first word in common, 001E. And then we take a look at the second word, so FC, FB, FD, and FF. So FB is lower than all these other ones right here. So this will be our, our root bridge. So we'll just mark all of his ports as forwarding. Okay, then when we look for root ports, right here we can tell pretty quickly that his direct connection of gig is going to be his root port. That's a cost of 4. Any other path will be higher than that. So that will be his root port. When we take a look at this guy down here, his root port, I think we can safely say it's going to be one of these fast Ethernet links right here, which is 19. Any other path he takes is going to be something higher than 19. And because the cost is the same, he's going to take a look at the BPUs he's receiving. And the BPU he received with a sending port ID of 5.3 is going to be preferred over the BPU with a sending port ID of 5.4. So this will be his root port. And if we take a look up here at this guy, I think we can tell that this is going to be his root port because 4 and 4 is 8, and 8 is lower than 19. And we know the opposite side of a root port is always a designated port. And we're done. We don't even have to figure out the rest of the topology. So now we know. Oh, and by the way, you might say, well, what about a port that's going to a host? Well, if you just do process of elimination, that can't be a root port because we're not getting any BPDUs on there. It can't be blocking, because if it was blocking, this host would have no network connectivity at all. So it has to be a designated port. So ports leading to hosts are always designated ports. But now we're finished. We know that between A, and B, there is only going to be one path that's open end to end. And if I, let's see here, make this a little bit larger, we can see that in this case, the path looked like this. It went through here, then up through here, and then over through here, up through here, and then across. Every other link was blocking somewhere. So that was the solution to that review question. So at this point, I think you guys are going to be experts at figuring out or deciphering spanning tree topologies. Before we bring this session to a close, does anybody have any residual questions for me? All right, well, I don't see any other questions coming in, so I'm going to bring today's session to a close. I will keep the YouTube live session up for another 5 or 10 minutes. So if you do want to post any additional questions or comments in those 5 or 10 minutes, I'll do my best to respond to them. But I'm going to close out the video portion right now. So thank you everybody for watching today. Hopefully you feel a lot more confident with your knowledge of working through spanning tree, and I wish you the best of luck when taking your CCNA or CCNP exams, and keep in touch. Watch out for future shows that we'll have in the future. So have a good weekend, everyone.